Welcome everyone back to 264A Automated Reasoning. And this is our lecture 9. Today we will be covering two subjects. In the first part, we will be zooming in on a new tractable circuit type, which is the NNF circuits that we obtain by combining determinism and decomposability. And that's known as deterministic decomposable negation normal form. It's a pretty influential type of circuits, in particular to probabilistic reasoning, as we will see. And then in the second part, we will go and start talking about knowledge compilation. How do we convert Boolean formula into tractable circuit types? And there we'll see that there are two kind of methods for that, top-down and bottom-up. We got a hint of bottom-up last time, but today we will focus on top-down compilation, which is related to what we've studied when we did SAT and DPLL. After these subjects, we will be zooming in on two more circuit types that are based on decision diagrams. Those are also very influential, and in relation to that, we'll talk about bottom-up compilation because they're typically compiled that way, or at least that's how things started there. And that will basically be the end of our foundations part. So let's go ahead and go to the whiteboard and get started. All right, so as mentioned, we will be focusing today on the property of determinism. And when this is combined with decomposability, it leads to a circuit type that's notated that way. And again, here's the big picture. So we're basically looking at one more circuit type in this box, zooming in on it, and we'll see that it enables something very specific and makes it quite influential because of that. And as I mentioned earlier, then we will talk about this compilation process, at least one aspect of it. All right, and remember, we've been looking at these circuit types from two angles, the kind of queries that they enable in polytime, and then the kind of transformations that they enable in polytime. So towards the end of the segment, we will revisit these and give you a summary of what happens to these operations and transformations when we have both decomposability and determinism. All right, so since we will be combining decomposability and determinism, let's start again by a quick review of the decomposability property, which we focused on last time. This is a negation normal form circuit. We've got the literals at the bottom, and then we've got ands and or layers. That's negation normal form. Remember, as we mentioned last time, you can have actually constants at the leaves, that is true or false. Typically, we don't start with these, but you start getting them when you condition. And as you remember, decomposability relates to AND gates. So the idea is you look at the subcircuits that are feeding into the AND gate, and they shouldn't overlap as far as the variables that appear in them. In this case, this subcircuit has AB, and in this case, this circuit has CD, and then they do not overlap. And you need this property to hold for every AND gate in the circuit, and when you have that, you have decomposability, and we call the circuit type d-DNNF. Now, we will be focusing on determinism today and the impact it has on tractability. And if you recall, determinism actually related to OR nodes. So if you have an OR node like this, and in this case, it happens to have two children, let's call the first one alpha and the second one beta. Then what I want is alpha and beta to be mutually exclusive. One way to look at this is to say what I want is alpha and beta to be inconsistent or unsat. Another way to look at this is to say that they shouldn't share models. And if I had a third, let's say, child gamma, then this should hold for every pair of them. Then alpha and beta shouldn't be consistent, alpha and gamma shouldn't be consistent, and beta and gamma shouldn't be consistent either. So all of these should be mutually exclusive, every pair of them. And you need this to apply for every OR node in the circuit. And if every node in the circuit satisfies this, then we would say that the circuit is deterministic. This would be a deterministic negation normal form. Now, we will need another property, which also we talked about last time, and that is smoothness. And this is a convenience property, as you will see. It is really not strictly needed for polynomial complexity, but it simplifies the algorithm. I'm going to review it first, and then when we get to using it later, you'll see why it is convenient. What is smoothness? Again, let's go back to calling this alpha and calling this beta. What I want is those guys to mention the same set of variables. So if I look at the subcircuit alpha and see what are the variables that are contained in alpha, I want these to be the same as the variables that are contained in beta. And if I had another child gamma, then similarly. So in that case, alpha, beta, and gamma, each one of them should mention the same variables. You'll see later, it's easy to enforce this. If your circuit does not satisfy this, you can actually make it satisfy this property relatively easily at most quadratic time. And again, we will see why do we actually need this particular property. All right, folks, so let's just remind ourselves of the acronyms, and then we will move on to see what reward do we get by adding determinism. And these are the acronyms. The first one is what we looked at last time, is DNNF, which is Decomposable Negation Normal Form Circuit. And then the small d is usually for determinism. And when we add smoothness, we get this small s as well. All right, the first thing that this enables is that now we can do model counting in linear time, except what I want in this case is I want you to help me discover this algorithm. So remember, we looked at model counting. We refer to it as CT in those tables that we were developing. And we saw that we cannot do this with decomposability alone. And then we now we'll see that if you combine decomposability and determinism as properties, then the circuit types will allow you to do model counting in polytime. Before we move on, let me ask you one question here. We said that this is important for which, or what complexity class does this correspond to when you start doing model counting? We talked about 4 classes, NP, PP, and then other ones. Okay, someone's saying PP, good. And what is the main application for counting? If you're able to count, and in particular do weighted model counting, can someone remember what was the main application we discussed for that? Okay, we did the reduction from a Bayesian network to a Boolean formula with weights. And then we said if we can do weighted model counting on that formula, then we can compute probabilistic quantities. Right, the application here is to probabilistic reasoning and as someone saying computing marginal probabilities. Excellent. All right. So folks, the claim is that we can count now the models of this formula or the circuit in linear time. And you saw what happened last time. Basically, every algorithm we looked at had the same kind of structure. You do certain things at the leaves, and these are the base cases, and then you move to the more complex cases, and we only had 2 of them. What do we do at AND nodes? What do we do at OR nodes? So if you want to come up with one of these algorithms, you start with the base cases. Literals, constants, and then you move up. And remember, the fundamental thing here is anytime you're looking at a case, you pretend that this is the whole knowledge base. So if I tell you what you are going to do on literals, and you pick this guy and you pretend that's it, your knowledge base simply has a sentence that says not C. And then you say, what is the model count in that case? And then you have the ... and then of course you can look at true as well and false as base cases. So question, this thing, all I know is not C. What is the model count in this case? How many models does this formula have? Okay, and people are saying 1. I can only satisfy it in one way by setting C to false. And similarly for a positive literal. So if I have the literal D, the model count there is also 1. because there's only way to satisfy that formula is to set D to true. So as you can imagine, for these guys, all of them, literals, positive or negative, will get a model count of 1. This guy will get a model count of 0, and this guy will get a model count of 1. So true is basically have a trivial model, which doesn't have variables in it. All right, so we have that part, and let's move up. What happens at AND gates? If you have alpha and beta, and I give you the model count of this and the model count of that. Remember, we have decomposability. So this would be over some set of variables X, and this would be over some set of variables Y, and these guys do not interact. They do not overlap, right? So this intersect that equals the empty set. So I give you the model count of this, I give you the model count of that, and I say, what is the model count of the conjunction? And I need to know what to do. And if you remember from last time, the way you want to think about it is what are the models of the conjunction as a function of the models of alpha and the models of beta. And someone already wrote the models of this whole thing is just the Cartesian product of these models with that. So actually all I need to do is multiply. So if you tell me this guy has 3 models and this has 2, every pair will end up being a model of the whole thing. So I take 3 times 2, and indeed you end up multiplying in that particular case. Now, what about the other case, which is alpha or beta? What happens in this case? I give you the model count for alpha, and I give you the model count for beta, and I want you to combine them so I have the model count for alpha or beta. Right, so I tell you this guy has 4 models and this guy has 5 models. What can we say about the models of alpha or beta? This is a deterministic circuit. So whenever I have alpha or beta cannot overlap. They're mutually exclusive. All right, now someone's saying, now we should sum. So just take the models of this guy and the models of that guy and add them up. Now, this is not true in general. But it's true because we have determinism, because the circuit is deterministic. And when the circuit is deterministic, anytime you have an OR node, let's pick this guy. If you look at this as alpha and this as beta, they're mutually exclusive. All right, so now you see what's going on. And you see the strong connection between these properties and probabilistic reasoning. So indeed, we multiplied these guys, we added those guys, and we can think of this as really evaluating a counting graph, if you want to think about it, right? All I did is I replaced the ORs with summations and the add with multiplications, and that's what I have. Let's count the models here. So I start at the bottom, everything gets a count of 1, I multiply, I add, I multiply, I add, and I'm getting the number 8. And this number 8 is basically telling me that this circuit has 8 models. Now, this circuit has 4 variables, A, B, C, D. That is 16 possible instantiations. And now I'm getting that half of them satisfy the formula. Actually, we looked at this circuit before, and I told you, I think that this circuit happens to represent the odd parity function. That is, a model will be satisfying if it has an odd number of variables set to true. And since the number of variables is 4, that happens also to be the even parity. So the models for this guy, because we're going to do a bunch of examples with this circuit next, so I want you to visualize the models. One of the models would be basically, so we have A, B, C, D, and if you want to set an odd number of these guys to true, you could have one variable set to true and the others to false. That gives you 4 possibilities. Or you could have 3 of them set to true and the other to false. That gives you another basically 4 possibilities, and that's the 8 models you have here. All right? Okay, now we need to take just a quick look here. So you could see why decomposability and determinism were important in this case, right? To sum the model count for this and the model count for that, I needed determinism because I needed to make sure that no model of this guy and no model of that guy overlap, Otherwise, I'm double counting. Remember when we did very beginning basics, and we looked at, you know, the models of a formula? I said, in general, this is alpha. In general, this is beta. And they could share models, but if they're mutually exclusive, that is, if their conjunction is inconsistent, then that area is empty and there is no overlap. So if I give you the model count for this, the model count for that, in that case, you can actually go ahead and add them up. Okay, so that was needed. And similarly, we needed decomposability to be able to multiply, because I'm assuming here when I multiply, I'm assuming that every model of this can be combined with a model of that to obtain a model of this. This is not true in general unless they do not overlap, because it's possible that one model of this and one model of that may clash if you have interaction. The question you probably is asking, why did we need smoothness? This counting that I mentioned here does require smoothness, and the procedure that we mentioned now will not work in general without smoothness. So let's take a quick look at that. That sometimes confuses people. First, let's look at why decomposability and determinism help us do what we did in a different way, more algebraically than using circuits. And here's a circuit or a function, Boolean function over 4 variables. And when you have it in negation normal form, it looks like this, right? So I have a disjunction. In this case, the OR gate has 3 children. And in each case, I have it decomposed like this. And basically what we just said, because we have determinism, the F1, F2, and 3 are all mutually exclusive, pairwise mutually exclusive. So we have this. And that's why if you give me the model count of F1 and F2 and F3, I can just add them. And the other thing we did is, well, if I want to get the model count of F1, I can get the model count of G1 and H1 and multiply them because they're over a different set of variables. So we actually wrote this, and that's what we did. And this is almost correct. For this to actually be correct as is, we also need smoothness. And what smoothness, if you remember, said that the F1, F2, and F3 should all be over the same set of variables. Now, this is true here, but let's see a situation where we don't have smoothness and how this may actually give you the wrong count and see why. Okay, remember, smoothness. Disjuncts must mention same variables. The main reason for smoothness is that it ensures we're counting over the correct number of variables. This is an issue we discussed earlier when we talked about model counting, but let's see it with a concrete example. So here's what I have. I have the function, and let's say the knowledge base is just A or B. Very simple, right? 2 variables, A or B, and as you know, this has 3 models, right? The only model that doesn't satisfy, or the only variable instantiation that doesn't satisfy this, is when A is false and B is false. That doesn't satisfy this. And the other 3 do satisfy that formula. Now, I'm going to rewrite that formula in 2 ways. Here's how I'm writing it. I'm writing it as A or, and then I'm putting not A and B. Right. Now, this is not deterministic, right? Because A and B do not conflict. But I can augment B with not A here. And those are equivalent, logically equivalent. But now I have determinism because now there's a conflict between these 2 guys, okay? But this is not smooth. Why? Because this disjunct contains only A and this contains AB, and I want them to contain the same variables. I can fix this. I can fix this by taking this guy and conjoining it with the trivial statement that says B or not B, right? This is true. So I just took true and something, and look what's going on now. Now I rewrote this in a way that is both deterministic and smooth. All right? Okay, there's hairy details, but it is deterministic and smooth. These 2 guys are mutually exclusive. Both of them mention the same set of variables. I have another OR here, and these 2 guys are mutually exclusive and mention the same set of variables. So now I have a smooth and deterministic. Okay, let's see what happens if I apply the procedure that I showed you earlier on this guy without smoothness, and now I apply it with this guy that's smooth. See what happens. So what did we say? We say add and multiply. And if you do this on this guy, look what you get. You get, what is the satisfiability of F1 the sharp SAT or model count these and add them. Now, what is the count of this guy? 1. And what is the count of that guy? That would end up being 1. 1 times 1. Okay, you get what? You get 2. That's an incorrect number. We know that this formula has 3 models. What happened here? What happened is, and this is something we talked about earlier, when I say count, in general, I have to tell you count over what variables, right? If I tell you count A or B over the variable A or B, that's different than count that formula over the variables A, B, C. And what we assumed in our procedure is you're counting over the variables that appear in that formula. So in this case, implicitly, I'm telling you count A over 1 variable. And I'm telling you count this guy over 2 variables. And that's why you get in trouble. If I wanted to do this right, I should have told you count this over 2 variables, and then you would have given me the number 2. So if we want to get this right, I should have passed the number of variables you're counting over. But smoothness says no. If you have smoothness, you don't even need to pass the number of variables you're counting over, because those variables are already built into the formula. So let's look at what happens in this case if we do this guy instead. Now I'm telling you count this guy, count that guy, and add them. And now B is in there. So when you do a model count for that, you get the number 2, which is the correct number. You add them, you get the number 3. Okay? So I introduced smoothness a while back. Smoothness, determinism, and decomposability. I introduced all of these about 2 decades ago. And I find out that people still use them, but don't understand what smoothness is doing here. And this is what smoothness is doing. And at some point, I gave a talk earlier in the summer to the database theory conference, and someone says, why did you call this smoothness? And I had trouble actually recalling. And then I drew this image trying to maybe recollect why I call this smoothness. So let's look at this circuit here, an OR gate. And here are the 2 subcircuits feeding into it. So this is smooth. If you look here, PA, and if you look here, PA, right? So the idea was you look at it this way, same set of variables. Now look at this guy. This is not smooth. You have P here and PA here, so they're not the same. And you get this picture, so that's rough. I don't know. Maybe that's what happened. And you can see how we made this smooth by simply adding this trivial gate. So you can basically add trivial circuits, and then you get smoothness. Okay, I hope this makes things clear. In just a little bit, we'll also link this to probabilistic reasoning. What I just showed you here is actually underlies a lot of what's happening in probabilistic reasoning these days on what people call tractable probabilistic reasoning. We'll have a lecture dedicated to this later, but let me just throw some names or some terms that some of you may have heard. So if you've heard about things, arithmetic circuits or some product networks, or these days people talk about probabilistic circuits, all of these are based on what we're talking about here. In fact, the delta between what we're talking about here and this thing is like epsilon, is very little. This is the foundation of all of this. This is actually what started all of this. And we'll make a connection today and elaborate on it later as well. Let's move on. And what I want to show you is you can do even more sophisticated type of counting. Now, I want to do what I call marginal counts. All right, so it's not just counting how many models a formula have, but I want to count how many models satisfy a certain property. So I want to know how many models set A to true and set B to false. Well, there's 2 ways to do this. The obvious way, and then I'm going to show you a less obvious way, and you'll see why. But the obvious way is you go and condition this formula and say, well, let me condition it. I want to set A to true and set B to false. And that's what we did here by replacing these with the values. And let me count, right? So now I'm counting that part of the formula in which, or those models in which A is set to true and B is set to false. And actually, can you predict the count in this case? Remember, the original formula is the odd parity. Every model has an odd number, 1 or 3 variables that are set to true. So if I set A to true and B to false, I'm only free to choose now C and D. I'm wondering if someone can actually predict what I'm going to get. Okay, a bunch of people are saying 2. Let's see it. And yes, it is a 2. Good. All right, you guys predicted correctly. Now I'm going to actually do this counting business in a slightly different fashion. Look what we're going to do. Instead of doing this, I'm going to treat these as variables. And I'm going to index them by the corresponding literals so I don't lose track of those variables. Okay, so I'm going to now view these as a circuit, a computation graph. And these are inputs, they're variables. So now the computation graph can be thought of as a function of that many variables, right? Then you see why we're going to do this. Now, let's go ahead and try to see what we're doing here. So if you come and tell me, I want to count the models in which A is true and B is false, I'm going to tell you, well, here's how you set these inputs to the circuit. I'm going to set the values of these variables in the following way. If the index or the subscript is consistent with this guy, it gets a 1. If it is inconsistent, that variable gets the value 0. That's actually what we were doing before. So let's try it out. In this case, those indices or those subscripts are incompatible with that. So they get zeros. Every other subscript is compatible. It gets a 1. And just let's go ahead and count. 2. We're good so far? No, now I need to know how many models have A true and B false and C true. All right. And let's try. So what happens? Okay, now this guy also becomes a 0 because it conflicts with this. And then I evaluate, I'm going to get a 1. Okay. Now, here's the thing. The thing is, this graph is a function of 1, 2, 3, 4, 5, 6, 7 variables. 8 variables. It is meaningful to talk about the partial derivative of that function with respect to any of its inputs. What is that? That is, how would the output model count change if I wiggle one of these guys? That's a meaningful thing, correct? And in fact, if you compute the partial derivatives for this output with respect to each input at this point, you're going to get these numbers. These are the partial derivatives. How do we do that? Using backpropagation, basically, like you do it in neural networks, right? So you can actually compute the partial derivative of the output with respect to each one of the variables. I did that computation for you. It's straightforward, but these are the partial derivatives. Now, why is that helpful? Okay, now we're going to see why it's helpful. Because of this technique, you can now answer not just get just the model count of the formula, but you can get a whole bunch of marginal counts all in linear time. You can get n marginal counts without having to evaluate the circuit n times by doing one pass upward to compute this guy and another pass backward to compute the partial derivatives. You're ready to answer n marginal queries. And for probabilistic reasoning, this effectively means you can get the marginals over all variables in the Bayesian network in linear time. Let's see how this works. Okay, so here I am, and let's say you tell me I evaluated the circuit. This is what we did, and I counted how many models have this in them: A true, B false, and C true, and I got the number 1. And now you come and tell me, wait a minute, I want to do another count. I want to see how many models have A true, B false, C true, and D false. Now, you have 2 options to do this. One of them is you say, okay, let me reset these guys. And what do you do in this case? You have to take this, flip it from 1 to 0, because this guy is now not consistent, and you evaluate the circuit, right? This is one thing you're going to do. The other thing you can say is, wait a minute, I do have the partial derivative of this with respect to that. That is, I know what happens when I change this by a certain amount. That's what's going on here. So you don't have to evaluate the circuit. You can go and just say, okay, the original was 1. The delta change here was from 1 to 0. That's -1 multiplied by the partial derivative. I get a 0. So you get the 0 model count in this case. And I didn't have to evaluate anything. Okay, let's take a look at another example. Here you are, and you already evaluated the circuit for this query. And now I come and tell you, you know what? I'm interested in the model count if I take out this guy. I don't want it. So I just want A true and C true, right? And similarly, the change that happened here is that you basically can flip this from 0 to 1. Then in that particular case, you can either reevaluate the circuit, but you don't have to because you have the partial derivative. And people are becoming expert about predicting the counts. So someone is predicting 2 in this case. Let's see. Yes, I have a change from 0 to 1. That's a change of positive 1. The partial derivative is 1. Then the model count is 0. So I got that. Now, someone is asking again, how do we compute the partial derivatives? I didn't show you this. It's a simple procedure that walks back through the circuit. And it's like what people call backpropagation in neural networks. It's the same procedure. So we're skipping that for now. Let's just say you have them and you can get them using one pass over the circuit. Let me just make one more remark and then show you the summary tables for determinism, and then we'll say a little bit more about it, in particular in connection to probabilistic reasoning. I need to make one more observation before I show the summary tables, which is, can we existentially quantify from these guys? So far we only did counting, and that's pretty important. Very important. We spent so much time on it because, as I told you, there is probabilistic reasoning or exact probabilistic reasoning. Now, what happens with existential quantification? Now, we saw that with decomposability, we can easily existentially quantify any number of variables. And we do this by simply replacing their literals in the DNNF circuit by true. And the idea was the result ends up also being DNNF. So you take a DNNF, existentially quantify any number of variables, you get a DNNF in linear time. Now this is a DNNF already, right? So it is deterministic and decomposable. So it is this plus determinism. But since it is already this, I can do that procedure and I say replace this by true, replace this by true, and I do that. What you get is correct as far as being equivalent to the existential quantification of P from the original circuit. So it's a correct circuit. It's capturing logically the same thing. The question is, does it remain to be deterministic? Because when we say you can existentially quantify a variable from a deterministic decomposable in linear time, that means I want you to guarantee me also that the output is of the same circuit type. And in this case, you can't do that. The resulting circuit is only guaranteed to be decomposable, but it's not guaranteed to be deterministic anymore. And you can get a hint of why that is the case. I lost the ability to actually have a conflict on these guys because of that. So you actually can't existentially quantify from these guys easily while preserving determinism. And I hope you saw what's going on. So let's look at the general table here. These are the queries. Remember, we're talking about here not just determinism, but determinism plus decomposability. So this is basically a subset of DNNF. And as such, these are queries. Anything that can be done easily on a DNNF should be doable easily on this guy, right? Because I just added one more property, and therefore I'm looking at a subclass of decomposable negation normal form. So a lot of these things were already there because we could do them anyways. These three were already inherited from decomposability. Now we have three more things. This we already talked about, so you know that. And what about validity? We didn't talk about validity, but the claim is now you can check validity easily. Remember, what does validity mean? Validity means that every truth assignment satisfies the formula. That is, if you have a formula over n variables, then the model count is 2 to the n, right? That's validity. So if you know how to count models, you can count the models with the formula and see if that ends up being 2 to the n. So you can actually get this because of counting. And this we didn't talk about. This is checking whether a term implies the formula. We're not going to do it. You can see that in the knowledge compilation map paper, or try to think about how you can derive it yourself. We can't do this. This is an open question. And if you look at transformation, doesn't look fantastic. If you condition, you still get conditioning still preserves determinism. We talked about it preserving decomposability, but actually also preserves determinism. We didn't argue for that. And that's it. We lost the ability to existentially quantify variables. We can't do these. Negation is still open. And that's the story with these deterministic and decomposable negation normal form circuits. Now, the biggest deal here, the biggest news is doing counts and doing marginal counts. And since we have a few more minutes before the break, I just want to show you a little bit more on this. One more example and make a stronger connection to probabilistic reasoning. And we're going to get to this later. So here's another circuit. And we can deterministic decomposable, and we're counting the models of this guy. And, you know, as you know, we sum and add depending on whether we have sum or multiply depending on whether we have an AND or gate or an OR gate, and you do this, and you get a 9. So that means this circuit has 9 models out of 16. There's four variables here. And now marginal count, we already talked about this, you know how to do this. And if I do that, that is how many models, how many of these 9 have A true and K false. If you do that, you're gonna get the number 2. And now, what if I want to do weighted model count? Remember, when we wanted to do probabilistic reasoning, we needed to actually do weighted model counting. And these circuits allow you to do this easily. Instead of just passing 1s and 0s, you end up passing the weights of these literals. All right, and then you can use this to do weighted model counting. Now, here's the interesting thing. So you remember the reduction that we did. We took a Bayesian network, we wrote out a Boolean formula, and we attached weights to some of the literals, and we said, look, by construction, if you know how to do weighted model counting on this Boolean formula, now you can compute marginal probabilities. Well, how do I do that? I take that Boolean formula that I got from the Bayesian network, I compile it into a circuit that is decomposable, deterministic, and smooth, and I'm done. I'm ready to do weighted model counting. I'm ready to compute marginal probabilities. And here's how you do it. You have this guy, and you just go ahead and multiply at AND gates and add at OR gates. And now I can basically go ahead and do marginal queries. In fact, look, I mean, if that's all we're going to do, get rid of the gates. And what do you have now? You have this, what we called earlier, counting graph. I call these arithmetic circuits. I introduced this concept a couple of decades ago again. And we refer to these as arithmetic circuits because they have these multipliers and adders as opposed to a Boolean circuit. And if you do marginal weighted model counting, you end up getting marginal probabilities. And even though there are no gates here, Boolean gates, they're just multipliers and adders, you can still talk about decomposability and determinism and smoothness for AC. So there is this construct called an AC, or an arithmetic circuit, which is this guy. And if you get it, now you can do probabilistic reasoning in linear time. And you can do derivatives of this guy, as we talked about. This is an important construct because there are many reincarnation of this construct under multiple names these days. We're going to get to that later, but you guys know what's going on. And two more observations and we take our break. Not only can you use this guy to do marginals, you can also do MPE. So again, one of our students in the past, Hey Chan, showed that if you replace these multipliers, these adders by max operations, then what this circuit will evaluate is the probability of the MPE. That means the number you're going to get at the top will be the probability of the most likely instantiation. Remember, that was the NP complete query. So this will give you that, will give you the probability of the most likely instantiation. And he even showed that you do a backward pass on the circuit and you get an actual variable instantiation that actually attains that highest probability. In fact, you know that procedure for attaining the, remember we talked about subcircuits last time? We said a subcircuit, you start at an OR node and pick one of the children. Same algorithm. When you evaluate this, whatever max value here will be attained by one of the children. So you traverse the circuit back and you pick the child that has this, that gave you that max value. But if you visit a star node, you pick both children. And if you keep going backwards like this, the subcircuit that you're going to get ends up being a variable instantiation like we saw last time, and it's guaranteed to be the one that has the highest probability given your evidence. So this is the MPE linear algorithm on arithmetic circuit. And let me just end with this picture so that you can visualize everything. One of the outcomes of what you learned about these circuits is that if you have a box that can take a Boolean formula and compile it into a circuit that is decomposable, deterministic, and smooth, then you can actually do the following. You can take your Bayesian network, write out a Boolean formula as we discussed last time, compile it into a circuit that's decomposable, deterministic, smooth, extract from it an arithmetic circuit, and now you can do probabilistic reasoning in linear time on this guy. Pretty fantastic. And this is not just, if you want to try this out, there is a system called ACE. And there are other systems, but ACE is a system available online, developed by one of our past students, Mark Shavira, who actually does exactly this. So if you want to try this out, we leave it at that. Let's take our 10-minute break. We're already a couple of minutes behind. And then when we get back, we will start the subject of compiling Boolean formulas into different circuit types. So 10-minute break.